Well, greetings and good morning to all of you, but now it's time to get to work. To bring this into the field of blindness, I'll tell you two stories of two boys in Tibet who went to the school for the blind there, Braille Without Borders. One of the boys was asked, "What do you want to do when you grow up?" He said, "I want to drive a taxi cab." Well, he came back a while later and said, "I know I can't drive a taxi cab, but I can own one and I can manage a taxi cab company." He had a big dream, like you, Professor Herr. And so I would like to invite you to come up, tell us how you brought your big dream into reality, and help us get started with our thinking here today. Come on up and let's give Professor Herr a hand.
Thank you, Bill.
I'm here if you need me.
Well, thank you for that very gracious introduction, Bill. Just getting the technology primed here. Good morning. How is everyone? I'm very honored to be here. Thank you to Michael Ellenbogen for the gracious invitation to be here this morning. So today I'm going to talk about my personal trajectory. That includes a bit about my past exploits in mountain climbing, and a great deal about my exploits in technology development and invention. And I'll finish my comments on some stories and opinions and viewpoints on the future of disability, or rather the end of disability, that very bright future that we all envision. So let me begin. So as stated in the introduction, I was in a mountain climbing accident and suffered severe frostbite to my legs. And after months of effort, my doctors gave up the fight to save the biological limbs, and they were both amputated just below the knee. So I'm standing before you supported by artificial structures, carbon composite, titanium, silicone. I'm basically a bunch of nuts and bolts from the knee down. But I'm going to tell you about those nuts and bolts. And by the way, Michael Ellenbogen is a key investor in making these technologies available to many, many people. And I thank him for that. So after my mountain climbing accident, I woke up with a very different body. And I said, now what? I never forget the morning waking up after surgery, and the white sheet was pulled over my legs, and you could just see the new end of my biological limbs ending abruptly. I did not know of any person previously that had a leg amputation, so I did not know what to expect. So naturally, after about 2 months from the point when my legs were amputated, I went to a rehabilitation hospital, and I sheepishly asked my rehabilitation doctor what I would be able to do with my new body. And he said, he asked, what do you want to do? And I said, well, gosh, I want to drive my car, as a teenager, 17 years old. I want to ride my bicycle, and I most certainly want to return to my chosen sport of mountain climbing, as I had started mountain climbing at the age of 6, and it was just a life passion. And he, without hesitation, said, you'll be able to drive a car, but with hand controls. You will not be able to ride your bicycle, nor will you be able to return to mountain climbing. I was naturally devastated for a few hours, and then after crying nonstop, I realized that the doctor was speaking nonsense. And the first weekend at the rehab center, the physical therapists knew what I was up to, and they refused to allow me to take my new artificial legs home with me for the weekend. The second weekend, they were foolish enough to allow me to take my legs home, and I went climbing. My brother Tony and I went out to a local cliff in Pennsylvania. I could barely walk. In fact, I was recommended to not walk without crutches because the artificial limb was so fragile, made of plaster of Paris, that it would break under my full load. So I hobbled along and scampered along, but when I got to the vertical world of rock climbing, I just felt at home. It was just extraordinary. And even though it was a rock face that was not nearly as difficult of what I was capable of prior to my legs being amputated, I felt at home and absolutely exhilarated. And I quickly began to take the opposite view of my condition and my body than what society was telling me. Society was telling me that my life was over, that I was crippled, that I was weak, that I was somehow inferior simply because I had a different body. And I did not accept this view, and I flipped it on its head just because I'm that way. And I said, gosh, the fact that part of my body is missing is actually an opportunity, because in that void, in that space, I can create anything I want to create as long as it's consistent with physics, physical law. So as a young man, I imagined a future world of technology where there are bionic limbs and I could perhaps run faster than persons with normal physiologies. And perhaps my bionic legs would not look like legs at all. Perhaps they would have wings and I could fly. And perhaps we could imagine technology being so sophisticated in the future that we could end disability. Visually blind and those of poor sight can see, those of paralysis could move, those of severe depression could live a day without absolute dread and rather with hope. That's the world that I envisioned. So my first task was to design my new artificial limbs, not for the flat world of sidewalks, but for the vertical world of rock and ice climbing. And again, a blank slate. So I built all kinds of new feet to wedge into rock fissures, to penetrate ice walls. And I quickly realized that, gosh, I'm so fortunate that both of my legs are amputated, because now I can be any height I want to be. And funny and true story, in my first several weeks of undergraduate study, I decided to do the following experiment. Every day I went to my undergraduate institution, starting from a modest stature. I would increase my height by 1 inch every day. And the experiment was, how long would it take for someone to say, gosh, what's going on? And I got very tall. Granted, I wasn't popular. Almost that I could touch the ceiling for balance. And someone finally said, what's going on? And I said, college is a growing experience. So sad. Such a sad joke. So I'm going to transition to what I'm doing now. As stated in the introduction, I'm an MIT professor. And I recently established a new center at MIT called the Center for Extreme Bionics. It can't just be BionX, it has to be extreme bionics, right? BionX is just so ordinary these days. So what is BionX? Specifically, human bionics is this interesting interplay between the biology of humans, how we work, and design. So we can deeply understand the science of how humans work, human physiology, and that can inform the design of novel synthetic structures that emulate that capability. Or it can go in the opposite direction. In realms of synthetic biology, practitioners are designing new biology that nature has not come up with yet. So this is an extraordinary time in science and technology because we're indeed blurring the boundaries between humans and designed either biologic or synthetic structures. So a theme today will be the science of the human and how that's informing design. So the center has 4 initiatives. One is to get information in and out of the brain, the central brain. The second is get information in and out of the peripheral body. The third is how can we build body parts out of synthetic structures that emulate the mass, volume, and dynamics of the biological counterpart. And thirdly, how can we grow cells and tissues to repair the body or to grow new parts or new organs. So I'm just going to go through and give examples in each of these 4 areas, starting with brain I/O. So the brain, as we all know, is really ugly. It's a few pounds of very ugly invaginated pink flesh. But when we look inside, we all know there's this extraordinary complexity. Billions of cells, billions of connections between cells. But what's not largely appreciated is there's tens of thousands of different types of cells in the brain that do different things and that talk to their neighbors in different ways. And we do not yet have a clear map of all these cells and what they do and how they talk to their neighbors. So it is a profound opportunity, both for quality of life of humans, as well as an economic opportunity to, in this century, understand the brain, map the brain, and also to develop technological interventions to get information in and out of the brain. Largely, brain conditions are treated pharmacologically. You dope this very complex computer called the human brain with a chemical with often very unfavorable side effects. What people are thinking about, brain scientists and technologists, are how can we develop tools that have extraordinary specificity, where one could target brain cell types and even specific cells within the brain and turn them all on and off and in effect re-engineer the brain. So recent work by my colleague and co-investigator within the center at MIT is Ed Boyden. Ed is a very creative guy, and he recently had babies with his wife. And I think he was staring down at diapers one day, lots of diaper changing, of course. And he said, gosh, to map complex tissues like brain tissue, why don't we infuse a brain tissue sample with basically the building blocks of diapers, and then add water and blow that sample up at least by 100-fold, and then with standard imaging tools be able to map that tissue segment down to the nanoscale. And that's what his group did. And what one sees is extraordinary complexity and extraordinary beauty when you map the very morphology of brain circuits. The initial goal is to map the nervous system of small critters, like shrews, and then ultimately to map up to a large animal such as a human, and really create, kind of a roadmap that technologists can use to really ask the question for a given brain condition or a given means of or desire to augment the brain. Where exactly in the brain do we target? What cells do we turn on and off, and so on and so forth? So how many here have heard of the new emerging field optogenetics? Anyone? A few, yeah, great. So this field did not exist just 2 decades ago or so, and now it's being heavily pursued by researchers around the world. So what is optogenetics? So by analogy, imagine that we could put solar panels on a brain cell of interest, and then by shining light across the brain, we could turn that cell on electrically. So that's basically what's being done by optogenetic designers. So what these types of designers do is they hack nature. So they take a DNA strand from a single-celled algae, and using a virus, they target a cell type of interest. That cell type then expresses a light-sensitive protein, and then by shining light across the nervous tissue at a certain wavelength of light, one can also turn on the cell electrically and have control over neural circuits. Many applications, my favorite and the most advanced clinically is having to do with vision. So for people that have photoreceptor cell pathology, wherein light shines on the anatomy of the visual system, and there's not a conversion to electrical information in the brain. What optogeneticists said is, so why don't we target the next cellular level down, the bipolar cells, and give these bipolar cells this light-sensitive protein, effectively putting solar panels on the bipolar cells. And then when light naturally shines onto the anatomy of the visual system, there'll be conversion from light or visual information to electrical information in the brain. This was first evaluated on mice that are not able to see, and to see if these mice in this experimental protocol are attempting to navigate a maze, and they're swimming in water, which they don't like, so they're trying to get out of the water. And because they're not able to see, they're trying to get through the maze by a brute force search, by feeling the walls of the maze and finding their way through channels to a platform to get out of the water. So after optogenetic treatment, these animals could then directly swim into channels, clearly exploiting visual information. What's exciting is this strategy has recently been approved by the FDA, and a human clinical trial is beginning soon to attempt to use this optogenetic approach on humans with visual impairment. So imagine a world where we understand the brain, we understand the individual brain, not just the average brain. We can map John and Susie's brain, and we can image that brain in real time and then apply interventions to the brain to treat a whole host of conditions. Severe depression, schizophrenia, anxiety, on and on and on. What a great world that would be. Moving on to body I/O, getting information in and out of the body. So here's a dream that I have. I want to build an artificial peripheral nervous system. If we succeed, this will be a strategy to treat basically every limb pathology that's out there. So there's many components. What we want to do is control muscles in the peripheral, in the limbs, for example, artificially. So imagine a person suffered a spinal cord lesion and that person's legs are paralyzed and immobile. So what the strategy is, we first put sensors in the muscles, and those sensors measure the length, speed, and force on the muscles. To measure length and speed, what we're doing is we're putting crystals in a muscle called sonomicrometer crystals, 2 crystals, and what you do is you send a current to one crystal, it vibrates mechanically, it sends a sound wave down the muscle, and then vibrates its partner crystal. And because you know the speed of sound in muscle tissue and you have a clock on your computational element, you know the length of the muscle and the speed of the muscle as it's contracting and lengthening. And if you put an electrode on the muscle, you can also tease out force of the muscle. So we then pass wires from these sensors through the skin membrane to a button that sits on the skin that has electronics, computational elements, microprocessors, A to D, wireless communications, all that sits on the surface of the skin outside the body. We pass wires through the skin membrane using a particular strategy. It's a conduit where skin adheres to the conduit, so there's not a threat of bacterial ingrowth and infection. And then there's computational done, and we know a lot about what muscles do in walking and running, for example, how they're controlled by neural circuits in the spinal cord. So we actually, on chip, program in those neural circuits on an artificial computer that sits on the button. So you can think of several buttons spanning a limb, each talking to a set of muscles. And each button talks to one another in a wireless communication, and we can build up an entire artificial spinal cord and restore movement. So how do we actuate muscles? Traditionally, muscles are actuated electrically, and it does not work very well because when you stimulate muscle electrically, you recruit large motor units before small motor units. So what that means is the force is low, and as you turn up the electrical pulse, you suddenly get a very large force, when the muscle's activated naturally by the body's nervous system, you go small motor units, moderate, and then large. So the force gradually increases when you increase the activation. So it's a reversed order, and muscles fatigue, and you can't do a nuanced control. So I just told you about optogenetics. It turns out optogenetics also works with muscles and nerves. And we've recently showed, actually 2 weeks ago, that we can get proteins to express in nerves so robustly that we can shine light on the surface of the skin and get muscles to fire in a non-invasive way. So that's very exciting. So we're going to demonstrate this artificial nervous system very soon, actually. So great. Moving on to biomechatronic body parts. So I am, as I stated, I am wearing 2 bionic limbs, thanks to Michael Ellenbogen and so many other contributors. So how do they work? So each of my legs has 3 computers. They're not like your desktop computers. They're microprocessors the size of your thumbnail, and they cost a few dollars each. So each of my ankles has 3 of these computers. And each ankle has about 12 sensors that measure position, speed, acceleration, force, and temperature. Those sensory data go into these computers, and the computers figure out what to do, how to control a muscle tendon-like actuator that moves and stiffens and powers the ankle. So we actually studied with these mathematical models, again, the circuitry in the spinal cord, and we program that logic into the microprocessors. The idea being is if we get the biophysical controller correct, that you simply bolt this to a human with a biological body, and even though it's made of titanium and silicon and carbon, it moves like it's made of flesh and bone, and the human doesn't even have to be trained. It's completely natural. So when I walk, I'm going to move away from the mic now. When I walk slowly, thank you. I have a handheld now. My ankles behave like springs, as they should. So when the biological ankle moves slowly, the ankle behaves like springs. But the faster I go, you can hear my ankles more. The more power I get, and I can even run, jump up and down, and it responds in a very natural way. So I don't get feedback here, I'm going to turn this baby off. Yeah. So we've, for the first time in history, built a bionic limb that normalizes walking speed and metabolism. So what this means is if you put a if you put a box around a human being and you measure how fast they can walk and how much energy they use, you can't tell whether they have bionic limbs or normal physiological limbs. That's pretty cool. That's progress. The company, BionX Medical Technology, has fit about 1,300 people. Half have been wounded US soldiers. Moving on to a different type of wearable robot, exoskeletons. So I was at the US Patent Office years ago digging through a patent shoe. The US Patent Office really hasn't gone totally digital. So you actually go there and you handle physical paper items. So I was digging through this box that had exoskeletons written on the side of the box, and I came across a patent by an inventor. His name is Yagin. He worked in Russia in 1890 before communism under a Tsar of Russia, and his dream was to augment the Russian army by building these crazy spring clutch technologies that run in parallel with the leg. As far as I know, his vision, his mechanism was never built, but this was the first recording or publication of an exoskeleton to augment a human in something as common as walking or running. No one succeeded in the goal of augmenting a human with an exoskeleton until 2014. My group was the first to build an exoskeleton to do this. We built a foot-ankle exoskeleton that's basically an artificial calf muscle that augments a person with completely normal legs and lowers the metabolic rate that a person requires when they walk and the speed with which they can move. It's so profound in its augmentation that when a person uses it for just 20 minutes and takes it off, their own normal biological legs feel heavy, stupid, awkward, and slow. So I'm convinced that this is going to catch on. Finishing up with regenerative body parts, Bob Langer is someone I admire so much, and he's also a contributor to the Center for Extreme Bionics. He does regenerative medicine and drug delivery, so he grows things as well as puts things in the body. So one of my favorite projects from Langer's group is the repair of a spinal cord that's been cut. So they initially took a mouse and with a cut spinal cord where there's significant paralysis in the hind limbs. And then they designed a polymer scaffold and injected neural stem cells to bridge the gap in the spinal cord. And they had extraordinary results. And a profound restoration of movement in the previously paralyzed limbs. And everyone told Langer and his colleagues this would never work, and they tried it anyway, and it worked pretty famously. What's really exciting is this recently has been translated into humans. The FDA has allowed the polymer scaffold to be used, but not the neural stem cells, but still, the initial data coming from the first set of patients is very favorable. So the first patient would have been completely paralyzed from the waist down, and now he's able to walk with a walker. He has restored bowel function. It's really exciting and extraordinary. But just as an aside, I think that we have an opportunity to really make dramatic progress in paralysis and spinal cord injury by a combination of regenerative repair of the spinal cord break and then the artificial nervous system that I mentioned previously that would correct for any remaining pathology, given that the regenerative repair of the spinal cord isn't quite perfect. So that I see a really exciting future to end disability in that realm. So I want to finish up with comments towards the end of disability. So I hope by talking about this tech that I've impressed upon you, if you weren't already convinced prior to my walking to this podium, that we're going to end disability in this century. And I think that's a very conservative statement. I think largely disability will end 50 years from now. So that's very, very extraordinary to think about. Disability, we all know, is commonplace. About half the world's population has some form of cognitive, social, emotional, sensory, or motor condition. And because of poor technology or the lack of technology, disability is very commonplace. That does not have to be. You know, I always say that there's no such thing as a disabled person. There's only disabled environments, broken environments. You know, to make that point clear, you cannot with a straight face say that I'm disabled. I have the condition that my legs are amputated, but it's not a disability because of great technology. I run on dirt trails, actually. I play tennis, I mountain climb, I do whatever I want to do physically. If you're mean and you steal my legs from me, all I can do is crawl. Please don't do that, please. But with technology, I'm just completely freed from these horrific shackles of disability. So I think that's a narrative and that will occur throughout this century. We'll systematically eliminate disability after disability until we get to the day where disability is no more. To race towards that future, we need two things. We obviously need better technology, but we also need improved societal attitudes. And there's a bidirectional link between these two elements. So you can advance technology and mitigate disability, and that has a side effect of improving societal attitudes. And you can also improve attitudes, and that can drive technology. So what do I mean by all of this? So just using my body and my experience as an example. Again, I returned to mountain climbing after my legs were amputated, and when my legs were amputated, again, society told me that I was broken and weak. It's a story where my father, he did volunteer work at a hospital, and someone came up to him and said, "Gosh, I heard about your son. I am so sorry." I was like, my father said, "Well, thank you." And then the person said, "He wasn't married, was he?" And my father was like, "No, why?" And the viewpoint was that somehow, because I had a different body now, that it just would have been horrific if I was in a romantic relationship. That I somehow no longer deserved a romantic relationship or was beautiful enough to be in such a relationship. So just extraordinary, the attitudes. And the problem with that is too many people believe it. Too many people have unusual bodies. They're told that by people in society, and they believe it, they give up, they don't go into that creative process to figure out how to restructure their lives, their environments, how to advance technologies to blend their new body with what they want to do in life. So that was right after my limbs were amputated. And then I said, the hell with the doctor that told me I can't do anything except drive a car with hand controls. And I went into this technological development, developed my own legs for mountain climbing. 12 months later, after my limbs were amputated, I was climbing better than I had before my accident with normal biological limbs. And I just thought this was fun because I really wanted to mess with people's attitudes. And it got to the point where I had climbing colleagues threaten to cut their own legs off to compete. So that was a lot of fun. So a story about how much progress we've made. just in the last decade. So I fly a lot, I travel a lot, and it was around the time just after the Boston Marathon, I think it was a year ago, and I was racing through Logan Airport, and when I go through airports, I always either roll up my pant leg or wear shorts, because when I go through screening, I don't want them to yell at me. I want them to see that I have bionic legs, so that they don't say, "Take your shoes off." So as I was racing through Logan Airport, I had 4 people stop me and say, "Did you run the marathon?" And with the glee in their eye, they thought I ran the marathon, and I bet they thought I may have won. Just 10 years ago, that would never have happened. We're making just profound progress because of technology getting better and our attitudes getting better, both hand in hand. When you see a person with an unusual body, for example, a person without limbs or whatever, what should we see when should we imagine in our minds when we're confronted with such a person with an unusual body? In the past, a normal person has pity in their mind. They say, "Oh, that person's life is over." But I'll tell you what I see in my mind. When I imagine a person with an unusual body, I see potential. I see incredible potential. We're at that point in history where we're transitioning, where there's a change and shift in consciousness that really I sensed as I walked through Logan Airport, that of a full acceptance of a person with an unusual body, and an embracing and no longer viewing such a person as weak and as ugly, but as a person that has extraordinary power, a person that can profoundly contribute to society. That's the dream that we all envision and that we're all working towards. Thank you very much.